Let's look at section 13.11, a Lewis acid-base model. Lewis acid bases are just things that are looking at things from the electron's point of view. So H plus is going to be a Lewis acid, just like H plus would be an acid in any of our models. And here the ammonia is going to act like a Lewis base, and the base is going to donate some electrons over here. So the base donates, kind of how I remember it. The acid with an A accepts. So the acid is going to accept these electrons. Now that I've moved electrons from one thing to another, I have formed a bond. Right. So remember, we got our three models for acids and bases. Arrhenius, which is the H plus producer, and OH minus producer, only going to really work in aqueous solutions. You got the Bronsted-Lowry, where you're looking at things from the proton's perspective, whether you're donating a proton or accepting a proton. And then you got our most broad, the Lewis, which is the electron pair acceptor for the acid, and a donation of the electrons for a base. The Lewis model advantage is that it covers many reactions that do not involve Bronsted-Lowry acids. So, example, gas-phase reactions between boron and trifluoride and ammonia. Right? There's no hydroxide that's being formed. There's no H plus that's moving around. Still, it's going to act like an acid and a base. So my base, my Lewis base here, is going to move some electrons over to this boron, and now I'm going to form a bond as I've moved those electrons around. When you start to do organic chemistry, this arrow convention, this moving of electrons around and representing it as an arrow, is going to become really, really commonplace. So this is probably the first time you've seen it, but when you see these arrows moving from one place to another, that's the movement of electrons. So here, water is going to act like a Lewis base. It's going to donate some electrons over to the Lewis acid, SO3. So if we're looking at the reaction between a covalent oxide and water to form a Bronsted-Lowry acid, that can be defined as a Lewis base acid. So this is showing how that Lewis model is still going to work in a Bronsted-Lowry acid. So when we form that bond there, we're going to form an additional bond between the oxygen and the sulfur, right? And we're going to have an SO bond that is made. Right. So let's do an example. Let's identify the Lewis acid and the base in the following reaction. We've got Ni2 plus and 6 NH3. So remember our NH3 molecule going to look like this. Nice lone pair of electrons here. So what do you think is going to happen? Yeah, that's right. So the electrons on the Lewis base are going to get donated to the Lewis acid, and we're going to form a bond. And those Lewis bases are then going to form a covalent bond over to the nickel. So the nickel ion is the Lewis acid, and the ammonia is the Lewis base, right? And ammonia, as you know, is basic. Right. So here's a strategy. When analyzing an acid-base equilibrium problem, ask the following questions. Right? What are the major species in solution? What's their chemical behavior? What are the major species that are present? Does a reaction occur that can be assumed to go to completion? And what equilibrium is going to dominate in solution?